Good afternoon, everyone. We'll give folks a moment here to get online with Zoom. I think we've got a number of folks planning to join us today. Some of the same old familiar faces, or names, I guess you could say, on Zoom on the right. All right, we will get moving here. So welcome back, folks, to another series here, the Critical Canadian Building Science series, carried by Building Knowledge Canada. We've been asked on several occasions, various events, various projects we've worked on, to start to look into some of the challenges and opportunities around electrifying homes, specifically part 9. And of course, new homes is one thing, existing homes another. But today we have some very special guests with us, joining us today. The title of the session today is, Challenging Future Electrification. What are we looking at? We've got things like heat pumps for space. We've got air to water systems, heat pump hot water systems. We've got electric vehicles that are likely going to be plugged into the homes that we're building. We've got homeowners that are going to want renewables. We have battery storage systems now in play, smart panels, all these types of things. And so we've got the experts with us today. They're going to speak to, number one, what do peaks really look like? One of the big, I'm going to say boogeymen, if you will, in the room is always, what's going to happen when we electrify homes? Is the grid going to go down? What's going to happen with the peak loads? And we do know that there are some real challenges because we are going to have some brand new peaks. We're going to move from typically what we would know as a peaking in the summer on the electrical grid to potentially some very significant peaks in the wintertime. But how much? So we're going to have some folks show us on that. We're going to talk about some of the opportunities to shave down some of these peak loads. And then we're also going to talk, Will Beardmore is going to speak to us a little bit about the challenges today in Ontario that are being faced by builders and homeowners that are trying to do something a little bit more, but where those challenges are both on the utility side and the grid side. So I'll introduce these characters one by one. Lee St. Hilaire. Lee, it's good to have you today. Lee's been a great supporter of not just building science, but also work that energy advisors, as well as a lot of the work a lot of advanced builders do across Ontario and across the province. Lee works with Aidan Brookson. Lee and Aidan both have been involved a lot in looking at things like grid to power work with electric vehicles, working with the electric utilities, and a number of other research type projects. Aidan has done a lot of work lately, working with a number of energy advisors, working with CanMet, as well as the Canadian home builders, to design tools that actually allow energy advisors as well as builders to look at their peak loads. For years we still use programs like Hot 2000 or some of these others, but we were never really able to assess the peak load or the peak load profiles. And now we have tools that can do that. So we may be introduced to that. And of course, many of you would know Will Beardmore and company have done an awful lot of practical support. Not only do they do photovoltaic design, Will, you do storage design, you do generation, you do community scale PV. I mean, Will's saying is, if you want a shark with a laser pointer, we'll get you a shark with a laser pointer. I sort of like that, right? You sort of put on the spot to provide the impossible sometimes. I've got myself just hosting you folks today. A couple housekeeping rules as we get into this is if you do have questions for the presenters that are topical, please put those into the Q&A. Stacy, who is with us today, Stacy Cooper, who runs our webinars, part of the BKC team, will help you line up those questions in the Q&A. If you have questions about the Zoom itself, the presentation, put those into the chat, and she's glad to chat with you there. Also note that Stacy's incredibly good too, that as things are mentioned, reference points, codes, resources, Stacy often will place those in the chat for you to go to as well. We do have a survey that comes out at the end of every presentation, so please fill that out. And just to say, as you all would know, the presentation will be shared, both a video recording as well as the materials, once the session is done. And it is those session materials and the video are also located on our website, the Building Knowledge Canada website, under resources. You can actually go back through now almost 2.5 years of critical Canadian building science, everything from vapor barriers to air barriers to mechanical sizing to heat pumps to solar to embodied carbon versus operational carbon, all sorts of good resources there that are nice little snippets that that your team can tie into. Closed captioning is available, so you can turn that on for yourself. Stacy, let's find out a little bit about these folks before we get going, though. I know where some of these folks are online today, but let's find out where they are coming from. Looks like we do have a few folks that are outside of the province today, too. Ontario is definitely leading the way. One of the things about the presentation today, folks, just so you know, is a lot of this is nationally reflective across Canada, some even beyond the borders of Canada, very similar challenges and opportunities in other places. But then there are also going to be some topics, especially when we get into some of the conversation with Will, that will be very specific to Ontario. And but again, lessons we can learn and maybe take away even in other provinces. Good. Excellent. So we've got about 80% of the folks are coming from Ontario. And then we've got some folks from British Columbia, Alberta, Quebec, Atlantic provinces, and even from the territories. Excellent. Well, welcome everybody today. Good to have you. The next question is real quick, and then we'll get on the way. What do you do? It's one thing to know where you're from, but it's a good thing to know what do you do day by day. And so we've got some architects. Got some energy advisors, some consultants. Other, if you are an other and you want to tell us what other work you do, feel free to put that in the chat. Got some building officials, mechanical designers, folks that actually build stuff, site supervisors. There you go. Good to have you folks too. Builder, renovators, developers, engineers. Excellent. Well, thanks, folks, for that very much. That's very, very helpful. And again, helps us understand the cross-section of folks that are interested in these. And always remember, on the surveys, feel free to put in topics, content. That helps us sort of explore what we can put on as we go forward, and topics that are of help, but also feel free to throw ideas in the chat too. So good. Thanks, Stacy, very much. Okay. I see Corrine's got her hand raised. Corrine, maybe I'll just let you, if you don't mind, we don't do over audio conversations. So Corrine, feel free. If anybody else has questions for Stacy, just put those in the chat and she can help you out. So before these folks get started, I'm going to show you the slides that everybody has seen and why we are at this place in this conversation. Number one, we know that we have a harmonized code that's going to come along at some point. We're all waiting with bated breath. And it's a energy-based code, and we know that there's tiers to it. We don't know really to the extent of where Ontario or how much Ontario is going to harmonize with immediately as of spring next year, or if they may give some time for harmonization. We're not sure. We're still waiting on that. But one thing we do know is that as the province like Ontario and others harmonize with the national codes, we do now have some set timeframes for where the national model code is going, and then the adoption period for the provinces And then in green, when the province will need to enforce whatever tier they decide on. So we have a tiered energy code. As of about 2 months ago, we also have work going on at Codes Canada around a proposed tiered operational carbon code. And then there's also work going on around some embodied carbon elements coming into possibly the 2030, along with some climate adaptability and resiliency in 2030. So this is the time frame. And the reason I put this in front of you is to say that there is nothing in here specifically, even at the codes level, that speaks to the requirement to electrify. However, we understand that by virtue of lowering energy, getting into reducing operational carbon, and eventually into resiliency and other things, that it does lead us down the path of moving towards higher and higher levels of electrification. And of course, there's also the building science side of it, exergy energy. We'll talk about that someday, that really to get systems in our homes and buildings and technologies that actually don't waste energy and that are low exergy systems, we really do have to move into electrification. So with that, I'm going to stop sharing my screen, and Aidan and Lee, if you want to tie in there and get it started with your presentation.
Thanks, Aidan, for getting that up. So I'm Lee St. Hilaire. My co-presenter today is Aidan Brookson. We've been around the block a little bit on the Part 9 world. Aidan, if you want to go to the next slide. But we'll give a bit of an introduction. We're going to talk about electrification and some of the context around it, both on the building side and on the EV side, so the transportation side, because that's a part of a building nowadays. And looking forward, what we're going to see beyond this. Next slide. So like I said, we're from Volta Research. We are a not-for-profit. We work doing research in the Part 9 space mostly, generally around energy consumption and the electricity system, as well as any other kind of systems that attach to the home. That includes vehicles now. That might include solar or any type of other generation assets or energy assets that attach to the house. We've done a lot of work in terms of building tools for energy advisors. So we've got our Volta Snap dashboard or tool that wraps around HOT 2000, but we've also spent a lot of time working in vehicle to grid and utility programs as well too. So we've done four demonstration projects on that, and we've also got a background in transactional energy and high-end modeling for residential space heating and energy systems as well too. So we've got a good background on this. Aidan, next slide. So why are we sitting here today? The real question is, how are we going to do this electrification thing? Electrification is coming. It's going to, like Andy said, it's going to be necessary to get the energy numbers down, and also to hit the operational emissions codes as well too. So really, that's where we're looking at, and it trends toward electrifying everything eventually. And we'll see kind of, there are a variety of scenarios of how that looks, but we'll see how that goes from there. The issue that this creates is when you're starting to electrify heating specifically, and when you're starting to deal with electrifying vehicles, you get into the utility space on peak loading. Now, in buildings, we generally are concerned, in code compliance, we're concerned with the energy consumption. We're concerned with the annual energy consumption. Even when we talk about net zero, we're talking about energy consumption annually. But what that really means to utility is that we're going to be using a lot of electricity at certain portions of time. When I say time, I mean 2 minutes, 5 minutes. That's kind of what the utility cares about. How much power is going across their wires and poles, how much thermal loading is on their assets from the stuff that's attached to it. In the case of housing and vehicles, the stuff is definitely going to use more of the thermal capacity, or even overload the thermal capacity of those assets on the system. So we're going to be really dealing with the utilities more than we have been in the past, especially the electricity utilities. And really, what's the solution to that? We need to plan for electricity as a system. So look at all the aspects of it and have them work together, just like we do planning for building as a system. And I'm going to pass this off to Aidan now, given this context, to talk a little bit about You know, this, as we look at the buildings like this, but as we look at the grid integrating with that, giving a bit of a background on the grid, so you understand kind of where some of the utility concerns are coming from on this topic, and what we can do in the building and in the transportation system, and everything working together, how to mitigate some of that and make everybody's life easier. Go ahead, Aiden.
Okay, thank you, Lee. Yeah, so, we're here today to talk about electrification of residential buildings. But I think before we dive into the details of that, it's important to know and understand where our electricity comes from, because while it might seem like, it's sort of one concept, not all electricity is generated in an equal manner. So what you see here are the different, the main different generation sources for electricity in Canada. So clearly and their resulting emissions per kilowatt hour generated. So on the right side of the graph, we see the 4 main fossil fuel sources that we use in Canada to produce electricity and their associated carbon intensity. And then in the center and left of the graph, we see the renewable resources that we use in Canada. Now, typically when we evaluate the carbon intensity of the grid, often the carbon associated with the renewable resources is ignored. But what I'm showing here in orange is the life cycle emission factor for each of those fuel sources. So I think it's, as we move towards things like embodied carbon, you can think of the life cycle emission factor in a similar manner. It takes into account the manufacturing of the equipment used to generate electricity, and so on. But at the moment, there are clearly some standouts that are, producing a lot more carbon than these life cycle factors. So these are sort of the key areas that we're trying to look at. Now, what happens is a grid's emission factor, its overall average emission factor, ends up being composed of the generation sources end up being a mix of those I just showed you. So the emission factor ends up being sort of a weighted average of the different fuel sources used. So this shows the emission factors for every province and territory in Canada, as well as the Canadian averaged emission factor. I've highlighted some of these in orange, which show you the grids that still produce electricity from coal. So you can see in general, these provinces have much higher emission factors. And then another sort of outlier here is Nunavut, which a lot of the electricity comes from diesel generation, which is why that emission factor is so high. And then those that sit below about 200, 100 use natural gas to produce electricity, and then a mix of other renewable sources. So if you look at Ontario, we use nuclear, hydro, natural gas, wind, and some solar and biopower. Whereas provinces like Manitoba and Quebec, the vast majority of their electricity comes from hydro. So that's why their emission factors are so low. So when we're talking about electrifying buildings, it's important to take the regional context into consideration. So what I'm showing here, it's a very high level sort of back of the napkin calculation. And we're looking at converting a natural gas furnace into an electric air source heat pump. So here we have an amount of carbon associated with running that furnace on an annual basis for, a fairly typical home might be around 3 tons of carbon per year. Using an air source heat pump and considering the low grid emission factor in Manitoba, we get an associated emissions of, effectively zero compared to what they were before. However, if we go over one province, which had a much higher emission factor, you can see that moving from natural gas heating to an air source heat pump can actually increase emissions in certain contexts. Now, this is important to take into consideration. I'm not suggesting that we don't install heat pumps in these jurisdictions. But what it means is when you install heat pumps, there are perhaps other measures that should go along with it. So one example, we could choose a heat pump with a higher COP. That's going to reduce the amount of electricity needed to run it. We could also pair that heat pump with solar, which is going to offset the electricity consumed by the heat pump and drop the emissions even further. So this is just to say that, it's important to think about, what's in the fuel that we're using when we're talking about electrifying our homes. So to make matters even more complicated, it's not just about where you use fuel, it's about when you use this fuel. So this shows the average emission factor on an annual basis for Ontario based on 2020 data. If we look at an average winter day, we can see some variation across the day, as expected, as demand ramps up. Natural gas peaker plants come online, it increases the emission factor of the grid. And in the summer, this impact is amplified even further as more air conditioners are being run. There is a greater demand on peaker plants, which ends up increasing the emission factor of the grid to upwards of double what the annual average is. And what's interesting is if we compare this to a typical residential baseload profile, so how homes, non-electrically heated homes would use electricity throughout the day, you can see that in the later hours of the day, there's quite a lot of alignment between when we are using electricity and when the grid has some of the highest carbon intensity of the day. And this is sort of, when you add an air conditioner into the mix, it makes matters a bit worse because we're adding another peak, between say 10 a.m. and 5 p.m., which is aligning with those high carbon intensive times of the day. And there's a sort of hot topic in Ontario right now because we're decommissioning some of the nuclear facilities here. And this just shows, if we were to replace all of the planned decommissioned systems, replace all that capacity with natural gas, we would be increasing our grid emission factor here in Ontario by quite a lot. So, there are things we need to do on the demand side, but on the supply side, there are also things we need to do to keep emissions low. So another interesting thing to look at is when we're talking about electrifying is how that impacts the price you're paying for fuel, for electricity. So in Ontario, we have time of use rates. So the cost per kilowatt hour changes throughout the day. This shows the winter time of use schedule, where green is off peak, red is on peak, and yellow orange is mid peak. And what I think is interesting about this graph is that we actually move at 7 p.m. We move to the off-peak time of use rate when emissions on the grid are still some of the highest they are all day, which is not exactly the price incentive structure that we might want if we're trying to price signal to reduce emissions. Ontario just released a new type of time of use schedule that uses ultra low overnight rates. I think they're as low as 2 cents a kilowatt hour, whereas the off-peak previous rate was about 7 cents a kilowatt hour. So you can see here there's much better alignment with those carbon intensive times of the day. It's worth noting, however, that I think some people have been doing some cost analyses, and it's actually hard to win out in this case as a consumer compared to the other time of use schedule, just based on where the exact prices actually sit. So now we can get, we know where electricity comes from. We can sort of get into what it means to electrify a home. So here on the right side of the screen, we've got technologies in a home that are traditionally electric. So that's space cooling, your air conditioner, and base loads. Now we're talking about, when it comes to electrification, we're actually talking about converting some of our largest energy consuming activities from a fossil fuel into electricity. So this just shows the potential peak load impact of different residential technologies. So if we're looking at a heat pump, we're adding a 3 to potentially 15 kilowatt load. With baseboards, it would be even worse because you're not getting the efficiency of a baseboard is 100%, whereas a heat pump is 200 to 300%. With hot water, a heat pump water heater, you're adding, a moderate peak load, and with a tankless non-heat pump water heater, you could be adding a pretty significant peak. And the same goes for electrifying transportation. So a typical level 2 charger, you're going to be adding maybe a 6 to 12 kilowatt peak load to your home. It could be as high as 19 kilowatts. But these are all things we have to plan for as we're talking about converting these technologies off of fossil fuels. So why is it important to reduce peak loads? Well, it reduces the strain on the grid, which improves the reliability of the grid, less outages. It can mean that it can result in lower emissions because the grid overall won't have as high a peak demand, which means we would need less peaking generation facilities. It can lead to lower capital costs, so lower peak load, smaller heat pump means it's cheaper to buy. And it can also result in lower operating costs for homeowners and lower associated emissions. And we can also scale these benefits out to the community level, which can potentially mean we save on sort of like larger infrastructure costs across the whole community. So now I'm going to dive into an example of sort of a kind of typical new construction home in Ontario. So what you see on the screen here is a heat map of the hourly electrical load over a year. On the x-axis, we have the day of the year, and on the y-axis, we have the hour of the day. So you can see, because this house, the only things that consume electricity are the base loads and the air conditioner, the electrical profiles in the winter and shoulder seasons are pretty flat. This is using the EnerGuide standard operating conditions for base loads, which is why they look so flat over the course of the year. But in the summer, we can see the peak loads that result from an air conditioner. So now let's look at what happens when we go all electric. So no improvements to the building. We just swap out the furnace and the natural gas water heater for their electric equivalents. So in this case, we've added an air source heat pump for space heating and a heat pump water heater for hot water, and we've done no other envelope improvements. So whereas before we were dealing with about a 1.5 kilowatt peak load in the winter, we've increased that to just over 7 kilowatts. So that's happening here in maybe late January, early February. And yeah, as Andy sort of alluded to, this means that we're introducing a new winter peak as we talk about electrifying space heating. And what's interesting here is the overall energy consumption is actually being decreased by quite a significant amount. So what we're trying to show here is there is more to these decisions than just the annual energy implications of a home improvement. There are a lot of other sort of metrics that we need to look at to make better decisions.
And Aiden, to
So,
interject here on this as well too, the important bit on that is, even though the annual energy reduction has been reduced and significantly, meaning a good movement through code toward higher tiers, the utility doesn't worry about that. They're really caring about the peak. They need to build out their system to deal with the highest electrical load that's going to come across that, because that's how they design a system. So it's very important to consider that despite moving up in code, depending on how things are designed and placed, you could end up being more infrastructure needed on the electrical side, which means infrastructure needs to be bought. Go ahead, Aiden.
Yeah. So if we go from this all electric case with no envelope improvements and then add some envelope improvements, we can see we've cut the peak load, the winter peak, by about 1.4 kilowatts. So in this case, I've essentially added R10 to the entire envelope and reduced improved the air tightness to 1.5 air changes. I did not improve the windows. That's why there wasn't a big change with the summer peak. But essentially what this means, we've reduced the electrical consumption by about 1.5 kilowatts. That can, in this case, it can mean 25% smaller heat pump, which can mean a lower capital costs when selecting a heat pump. This can also mean if in the initial case you might have had a bigger heat pump, it could have had the breaker could have had a 60 amp requirement. If you can reduce the peak loads of your home and then end up selecting a smaller heat pump, you could maybe cut that breaker size in half and end up with smaller equipment that way. Another example of how to reduce peak loads is through hybrid heating. So in this case, what we're doing is we're using the existing natural gas furnace below a certain temperature threshold. So, and then a heat pump, an air source heat pump above that threshold. So in this case, below -5, we're switching over to the furnace, and you can see that, again, we started at 7 kilowatts. We've cut it down to 3.4 kilowatts. And you can clearly see on the graph here, the dark blue in the winter months where the heat pump is turning off and where the furnace is making up the heat for the home. So this is a graph that shows the composition of the worst day of the year for the all electric, no insulation case, the composition of the electrical demand for that day.
And Aiden, you can where was the design location of this? If you can just add that in.
It was Guelph.
So climate zone 5 for those of you the geeks in the crowd that want to know the climate zone 5. There you go. Chicago, Detroit, you name it. Toronto.
So what we see here is we see this peak load that results from the heat pump, the space heating system, which is correlated to a pretty low ambient temperature. We're hitting -18 in this case. And this is just to show that, the load that we're introducing from a heat pump on the worst day of the year dwarfs the other loads in our building. So what I'm going to do is scale this graph. So this is the same graph.
And interjecting again, compare that back to the air conditioning load, right? So we're talking just over 5 and change kilowatts on that air conditioning load. It's not on this graph here, but Aiden had it up there before. And many of you, I don't know if you caught this, the Ontario people here, this late in the summer this year, we hit the highest loading ever on the Ontario electrical system. So highest peak loading ever experienced. And we're talking, electrical draws of 5 kilowatts and change from on average. running air conditioners, and we just see 7 here on the heating side, right? So we're talking, the potential for fairly large loading across the system. So this is an important thing to take away here. Go ahead, Aiden.
Mm-hmm.
Thanks again.
Mm-hmm. Yeah,
Love interrupting you.
Yeah.
That's good.
Yeah, so with this graph, what I'm going to do is I'm just going to change the scale. The content of the graph is not changing because now what I'm going to do is add the load associated with uncontrolled charging for an EV, essentially when a homeowner gets home from work. So they get home, they plug in their EV, and in this case, we add a 7 kilowatt load to the house at night. So again, this is another pretty significant load technology that we're going to have to manage and plan for. So before we dive into EVs, I just want to talk about how building better homes can help reduce the peak loads of your homes. So as you saw, the majority of that winter peak load is coming from the space heating system, which is, in that case, operating on the worst day of the year. So the space heating, the peak space heating load tends to be something that we would like to then minimize to lessen our sort of detrimental impact on the grid. So some of you might be familiar, CSA F280 is a calculation method for determining the peak heat loss and heat gain of a home. And what I want to show here is just how a couple different, energy conservation measures might impact the peak load of the home. So what you're seeing here is for the above grade walls, we're adding insulation. When we increase the insulation from R10 to R20, we're getting a 20% reduction in the peak heating load for the home. When you increase it another 10, we're getting a 9% reduction, then 5%. So we're getting diminishing returns on our on the peak load reduction for the same amount of R value added. Now, that's not to say you shouldn't build high R value walls. It's just to say that if you're looking to do something that reduces peak load, maybe if you're already at R30, an extra R10 to the walls might not be your best dollars per kilowatt reduced spent. There might be other areas that you could make more cost-effective peak load reductions. So one of those that's interesting is with the air tightness. So the results of a F280 calculation show that this tends to be fairly linear. The peak load reduction tends to be fairly linear with improvements to the air tightness of the home. So across this whole range, even at the more airtight homes, you're still getting about the same BTU per hour reduction per ACH improvement. So this is just to show that different areas of the home might have different implications in terms of peak load reduction. And as we design better homes, we should look towards where are the best dollars spent to result in reduced peak loads. So I alluded to this before, but EVs are going to be a huge component of our residential buildings' energy consumption moving forward. And with that, I will pass it back to Lee to discuss electric vehicles and the home.
Yeah, I mean, it's a really interesting change from where things were. We used to have gas stations, and gas stations kind of handled that component of fueling a vehicle. And now, based on surveys and kind of based on the industry data as it stands right now, the likelihoods people are going to be generally fueling or charging their vehicles at home. They might be doing it at work, but the likelihood is they're going to be doing it at home. And that means there's an expectation that they can do that at home, which means when somebody puts together a building, consumers are going to be expecting that it does the thing they want, which is allow them to charge their vehicles. Now, how's that kind of factor in? Well, that's a lot of panel load. Like we said before, that could be in the low 2-3 kilowatt range, but it's likely going to be in the 7-8 kilowatt range. Some of the bigger chargers, they're breaching into 12-15 kilowatt range, which is really interesting from a charging aspect of charging vehicles and kind of fueling them faster. It also makes panel sizing, subsequently infrastructure sizing on greenfield build out or even brownfield infrastructure a bit complicated. And you might say, well, is this stuff really coming quick? Well, it is. We have here the StatsCan data from electric vehicle purchases. So this is new vehicles only, right? We're looking at here. It's pretty similar to the other industry data that's out there from the standard market assessment firms. Look at that growth. We can see 2019 and 2020 on the left-hand side of the top graph there, and we're heading up to 2023, and we're easily doubling what we've seen in 4 years. That's approaching 10% of vehicles sold in Canada are either battery electric or plug-in hybrid vehicles, and the mandate's going to be 100% by 2035. And even if we don't get there, we're talking a large proportion. So we got to plan for this, and we can reduce the impact. Go ahead, Aiden. I want to come back to this unmanaged charging example. The green blob you see there on the graph, that is 35 kilowatt hours of energy at a 7 kilowatt charger. 35 kilowatt hours of energy, I'm going to put that in perspective of the vehicles on the market. That's an old Nissan Leaf. That's a vehicle that we would have considered, had a pretty low range. New vehicles, 4 times that, right? So a lot more capacity. So I'm talking about something that's at the low end of the market here when we're talking about charging. Now, realistically, people aren't going to burn the battery every single day. You're going to be, this is going to give you a fair amount of range, probably for your standard kind of back and forth to work if you work relatively close to where you live, or heading to the grocery store, that kind of thing. So I think it's an accurate 35 kilowatt hours is a fairly accurate number to use kind of for daily charging. So again, this is unmanaged. Look at that load, almost up by 12 kilowatts there. That's significant. That's that really is going to eat into that panel, even on a 200 amp panel, right? Definitely going to get us out of the 100 amp range, which means the rest of the build out has got to handle that. When I say build out, I mean wires, transformers, the high volt running between the transformers, the switchgear, and how hydro looks at that, right? So this is a problem. Next slide, Aiden. We got some solutions though. In the market right now is this thing called EV EMS. EMS stands for Energy Management System. The electrical code allows you to derate an EV charger down to 0% if it's controlled by an energy management system. This is the Canadian electrical code. Obviously, AHJ in each province has got interpretations of that. And Will can do a little bit of commenting on that as the expert there. But look at this. We've taken that 12 kilowatt almost load, and we've dropped it down to 7 and change. Basically held it at the peak load for the house. And that's pretty. We can do that today. That's a today solution. Go ahead, Andy.
Yeah, so just real quick, in my simple mind, you're talking about either a specific electric vehicle charger that does energy management in itself.
You got it.
Or a panel, a typical electrical panel that does energy management, not just for an EV, but everything else in the house, right?
You could do that too. And again, I'm going to let Will kind of talk about the code implications, the electrical code implications of that, because right now it's a little bit murky. Yeah. There's a clear call out on bulletins for the EV EMS right now. That's in the code. There's a rule. There's a clause for it. You can do it.
And when you say code, national or provincial?
National electric code. I have looked at bulletins personally from BC and Ontario, and there are little minutia bits of difference between interpretation on how that gets accomplished on the ground, but you can do it, right? It's allowed. And generally, it's been advertised as something that's used in multi-res retrofits, usually condos, other types of MURBs, just in terms of trying to get servicing for residents in a place where you've got a constrained, already in place utility asset. So you don't want to go and replace your panel board or the service to the building already. It's kind of a pain, right? But this can be applied across the community as well too. And I'm going to talk about a little bit at the end here about some of the things that we've got to work on as an industry when we have our discussions with the electrical utilities, because there's a bit of a different interpretation there in terms of how they determine load and how kind of we determine load as the building industry. But here's an example of what you can do. We got a good reduction, and that can be done today. I've got other solutions though too. Aiden, if you want to go to the next one. There's this interesting thing that's coming to market, and there's a couple of products in play right now called vehicle to grid. And vehicle to grid is essentially that charger can go both ways. It can take power from the electricity system and it can dump power back to the electricity system. In a context of a house, that kind of means power the house, right? And they can do all sorts of stuff. They don't just do that. Some of them do solar and some of them do smart panel type activities and all sorts of things. But let's talk about what it does to that load that we've been looking at throughout this presentation. We started at 12 kilowatts about. Let's say we want to hold that at 6 kilowatts now, capped. Well, we can do that. So on that green portion, we've still got the same kind of charging. It's just taking longer throughout that day. And that green hash portion is actually, we're putting energy back from the vehicle into the home to offset that peak, right? So we're looking at electrical infrastructure as a system. We're saying we want to hold that house at a certain value. We've got a bunch of storage that the owner of that vehicle has paid for. It's currently sitting in a garage or whatever, not doing anything, not making any money. And now we can use it to hold the whole load of that house at a certain point.
Wow.
And we have solved a big problem for utility system right there, right? So this is a really interesting technology. We've talked a lot about electrification barriers and constraints and problems, but we've got stuff on the market that can solve that. And Andy noted smart panels. Smart panels are very similar to the behavior of this. You could do kind of the same thing. Aiden, you go ahead.
So Lee, is this the reason why in a number of US states and in a lot of European countries too, we're starting to see the utilities offer not just incentives, but also outright purchasing this type of equipment, offering to put it in free of charge into homes, whether it's battery storage, whether it's bi-directional chargers, is because that is a less expensive way to help them manage the grid.
Absolutely.
Than would be to add another nuclear plant or a gas peaker.
Absolutely. Okay. Absolutely. It's a funny thing. So how all this works, because the utility says essentially, well, I need this capacity. The electrical utility says, I need this capacity in this region. And they go in Ontario, they go to the OEB and they ask them for some capacity. And the OEB says, you can put that in the rate at this level of return. They spend the money and they put the stuff in boxes, wires, poles, and more generation. And that's how they deal with capacity. But there are other ways of dealing with capacity issues too. And this is one of them. Smart panels are another one. Load reduction on the building by doing, a higher performance envelope. That's another one.
Yeah.
Right. So there are lots of ways to handle this for the electricity system without resorting to building more stuff on their side. Okay. Right. So and vehicle to grid is an easy one. We all know electric vehicles, the faster you can charge, the happier the person is. And that, and the higher the capacity goes up, the more energy you're going to have to put into them. So that's going to be one of the ones that's going to stick out, that along with the heating problem. So if we can kind of address both of those items, that's really helpful. And these are a couple devices that do this.
Yeah.
One on the left of your screen there, that's actually from a test installation that we worked on. That's about the size of your personal carry-on item on an airplane. The right-hand one is probably your technical carry-on suitcase size, right? So that's what we're looking at. The one on the right, and there's a few more that are available, but I've just got this picture. The one on the right can actually do a whole bunch of stuff. It can do backup for your house. It can do solar input without having a new inverter. It can do smart load control. It can also charge at 15 kilowatts, which is a pretty significant charge. So it's a really interesting device, and there's going to be a variety of them on the market very shortly. And they solve a lot of problems, both in the home and from the vehicle context. Go ahead, Aiden. And again, Andy likes to say for the nerds, but for the nerds here, this is kind of what the electrical integration diagram
This is for
looks
Will. You can see he just got closer to the screen.
He's like, what is that?
All right, let's see what happens now.
But this is interesting stuff. There's not much to it. Sub panel, transformer, device, everything plugs into it. For anyone who's seen what's involved in putting a battery system in, and the panels involved in that, or for a variety of the other vehicle to grid systems offered by GM, by Ford, there's a lot of infrastructure that's got to go into that basement, or wherever that electrical system's going. This is really simple. So it's a good solution, and it provides that all-important backup thing. We've asked people, we've done lots of surveying. Why do you want to connect your vehicle to the house? People want to have backup. They want to have backup their house. And you might think, well, why does that matter? But as we move toward electrification, as we move toward electrified heating and that kind of thing, people want to feel safe, that they've got a way to heat and cool their home, even if you all need electricity to run everything anyway. This is what people think. So there's a good pitch here for just the resiliency and comfort aspect of having these devices. Aiden, keep going, please. And what can you do with it? I'm going to give you an example. This is playing with that small device that I showed there, the black one on the left. So here's a graph of loads. This is over an hour or so period. Loads are in orange. They're positive. They're taking stuff. Washing machine, dryer, dishwasher, big stuff inside the house relatively, right? The blue is negative. It's the vehicle pushing energy back in. And then that purple is what you've got left, what you're taking from the grid, right? So we've gone from taking 6 kilowatts at the peak there from the grid when we're running the dryer starting off, down to just over 2 kilowatts when we pushed energy back in from the vehicle. Yeah. Right? This is minor. This is a minor push from that vehicle. 4 kilowatts is nothing. For people who are worried, what's that going to do to the vehicle? Think about how many horsepower your car's got, right? And let's say a kilowatt's about 3/4 horsepower. When you've got your foot to the floor on that electric vehicle, you're into the hundreds of kilowatts, right? We're not talking about much movement across that battery. So it's really not much at all to do this kind of servicing to a house. Aiden, next slide, please. What about another application? What about if you want to use that vehicle as a storage device and, buy low-cost power at night and then use that low-cost power during the day when the power is high? Well, you can do that too. This is an example of doing that on that device. This is, these peak and troughs. This is a day, essentially, right? Have bought it low at night, using it in the building during the day. We've shifted about 150 kilowatt hours using the vehicle. Now, what's the bonus of this? We've saved about, in this case, on Ontario time of use, standard time of use, we've saved about $12, $13 for that homeowner versus normal. You might say that's not much, but we've also reduced the emissions because we've been charging using low emissions, and then we've been discharging when the emissions are high on the grid. So we're also this is a few kilograms of emissions, but tack that up over a year and many years of ownership and many vehicles, that's a lot, right? And certain provinces where you've got variability, I think of Nova Scotia as one of them, where you've got wind and coal. This is a really great tactic to be able to reduce the emissions of that electricity system. So very interesting stuff. We're starting to get into the future looking now, and Aiden, I think I want to swap to the next side. Well, what is the future, right? What's the future going to need to get there? Well, I think one of the most important things is when your engineering firms, the electrical engineering firms are going to the utility and sizing all your infrastructure, and you're back and forth on that, well, they're using pre-canned loads that the utility provides or the utility wants to use. So there's some advocacy from our industry about, if we're putting in the effort to reduce our loads, we should be credited for that, so there's some of that work that needs to be done from a regulatory level. But we've got stuff in play right now. Energy management systems, again, smart panels, home hubs, vehicle to grid. These are all things that are available today. that we can put in the home to reduce peaking, as well as building a better home.
That's
Now
right.
there's the market incentives and stuff that comes along with that. Why? The money aspect, right? We're offsetting assets for the utility. That's a whole kind of kettle of fish that needs to be hashed out from the standpoint of where the money kind of transacts on that. And there are certain ways that the utilities are looking at that. So in Ontario, we've got these things called pilots called local capacity markets, which essentially says, I've got a region, it doesn't have enough servicing to kind of take care of all the load that's going to have. So we make this little market that deals with that region, and we price the price of electricity or the capacity you're providing to that region appropriately, which means it's a different price than say just time of use. In California, that's up to $2 per kilowatt hour. So there's some real value.
Yeah.
There's some real monetary value in doing this as well too. So that's being looked into. And I said Ontario, but that that kind of thought process is happening across Canada. We've got other interesting pilots. Electra Utilities in Ontario has done microgrid, or what they call a virtual power plant, which is a battery and some solar and controlled by the utility. And they credited back the homeowners some credits to spend at stores and stuff. Right. So that's an example. And Alexicon had a project with Marshall Homes and Opus One where they did a microgrid.
Yeah, Craig Marshall and team. Yeah.
Yep.
That's right.
So, and then looking farther along the road, how to get the money back and forth on this, you've got transactive energy, which is essentially users buying energy directly from producers. And we've got some stuff work in the US on that. We've got New Hampshire Electric Co-op, a big picture here of that. And they have a transactive energy market where vehicle owners can sell their electricity to users, sell their storage capacity to users. So there's some really interesting stuff coming down the road.
Yeah.
Some of this we can act on today. Some of this is going to be in the future, but certainly there's some space to talk about this. Yeah. And I'm going to pass it back to you here, Andy.
Hey, thanks, Lee Nate.
I've taken up time.
My brain sort of is swelling just a little bit. That's a lot to take in, but man, it's sort of cool. Will, Mr. Beardmore, you've been taking this in now. Here's a guy that has been telling us a lot of the same things. Will's been sharing a lot of this with us, encouraging net zero builders, net zero ready builders, folks and designers like ourselves and others to maybe it is better. I think Will would say, if that's okay, instead of just looking at how much you use over the year then trying to max out solar, why don't you right size the PV with a little bit of storage? Will, does that sort of make sense? I mean, am I putting words in your mouth or?
No, not at all, Andy. In fact, we've been advocating this, despite the fact that the more solar, the higher the project cost, the more revenue for us. We've been advocating smaller PV systems, right-sized PV systems, in order to encourage adoption and uptake, in order to put the technology in the hands of more people, in order to make it more accessible, in order to achieve the aims that we've laid out for ourselves at every level of government throughout the country.
Okay. Good, sir. Well, take it away. We are right at 2:00. So looks like we've got 11 questions already in the Q&A. So away you go. We'll do a wrap round. Yeah.
Yeah, I will. I'll go quickly, but hopefully not too quickly. I will say to start off that it was great to meet Lee and Aidan because, up until I met Lee and the project that they did, we've been very much sort of struggling with this stuff, with the deployment of technology like this on our own. And it's nice to know that there's others working at it as well. So, where we're coming at in this conversation is, there's a lot of conversation happening about what needs to happen, about technology that exists to facilitate the transition. However, from a regulatory and a code standpoint, we're not actually at the place we need to be in order to deploy this technology actually in the field, in reality. And so we encounter this every day, and it's a different challenge by geographic region. It's a different challenge by individual inspector and individual utility company. And so you know, it's a little bit of chaos and a little bit of the Wild West out there right now, and you know, it's hard to make commitments in terms of what we can and cannot actually do, because we never actually know what we're going to run up against until we call for inspection. So we're doing as much work ahead of time, behind the scenes, with multiple levels of government and outside agencies in order to try and make this thing a lot more friendly. But Andy, can you see this slide here that says distributed energy resources deployment?
Not yet. No.
Oh, damn it. All right. So then
While you work that out, Will, I was going to add in there as well too, to Will's point. If you're going to do any kind of project involving this, the best thing to do is start by talking to the, you know, your authority having jurisdiction on the electricity side, the utility. Have those conversations super early, super early, and get them involved, because that's how you're going to get stuff done. If it comes kind of at the end, it's going to be tough.
We saw it just a minute ago. Now we see a tent.
Are you seeing it now?
Nope, we see your screensaver though.
My screensaver.
Yeah, we did see it just a minute ago though.
Is this it? Sorry.
Nope.
I'm gonna stop sharing. I'm gonna try again. So we did actually test this beforehand.
That's all right.
Believe it or not.
Yeah.
Okay.
Yeah, we can see it now.
There we go, Will.
Yeah, feel free just to do it. There you go. Yeah, that's fine. We can see your notes too, but don't worry about it. It's
Okay, I'm just gonna go from here then.
all right.
There you go.
You would think I deal in technology all the time, and this is just one thing that eludes me, even though it's been many years of doing it this way. So anyway, so a couple of key things to cover here, just to put things into perspective in terms of what we're dealing with. So distributed energy resources, DERs for short. That's the terminology or the term that's important to understand. So, you know, the Ministry of Energy has overall jurisdiction. They established guidelines for the Ontario Energy Board. The Ontario Energy Board publishes the distribution system code. The distribution system code is essentially the code for utilities. So think of electric code for electricians, building code for builders. The distribution system code is the code for utilities. We have local distribution companies spread throughout the province. And so that's your Hydro One, Electra, Power Stream, et cetera. And then influencing electric code is CSA. And then we have the Canadian Electric Code, and that in Ontario and in other provinces translates down to the authorities having jurisdiction. And in Ontario, it's the Electrical Safety Authority, and then we have local municipalities. So when we talk about changing things, it's not easy. And it's not easy, particularly because a lot of these organizations are government, and that is the hardest and slowest to change, I think. Over on the right here, there's a table, and what we're showing here is classification of DER. So micro generation facility is less than or equal to 10 kilowatts max AC output. And this is important when we talk about all things, not just solar, but energy storage and electric vehicle supply equipment, in particular, the vehicle to grid stuff that Lee just covered. And I'm going to talk about that shortly. We're not.
Will, sorry, it's Stacy. Can you just click the from beginning button there, because people aren't seeing the full screen?
Well, if I do that, it goes to a different screen and I lose it.
Yeah.
Okay, because they're just saying in the chat that you are showing the secondary screen and not the main slide you're trying to show here.
I think he's gonna have to stay with that for now, though, Stacy. I just saw that comment too. Yeah, if that's okay, we'll get the full presentation out to you folks later.
You can see this slide that says distributed energy resources.
Yeah.
Though, right? Yeah. Okay. Yeah. If I click start from beginning, it goes to a different screen and I lose it. Okay. So connection process quickly for under 10 kilowatts. It's a simplified application. There's no cost for the application. There's no engineering requirement. It's a 3 to 5 day turnaround. It's a $400 to $800 average connection cost. Unless you're in Guelph, it's $1,500, or in Toronto, it's $2,300. There's no commissioning testing requirement. There's no engineer sign off. It's an ESA inspection, connection authorization, and then we energize. So very simple, relatively affordable. And the way things happen most for residential. Okay, and 10 kilowatts is an important number to understand, because that gets eaten up very quickly. You have a solar generator, so you have solar in the home, and you want to add a vehicle to grid EV charger, and you want to start supplying vehicle from your electric or energy from your electric vehicle back to the home, and you already have solar, it's going to put you over 10 kilowatts. Once we're over 10 kilowatts, the process becomes quite unfriendly for residential applications. It's an old process. It was designed for large commercial projects. It's a complex application process, requires engineering. So there's a design engineering component that typically looks like $3,000 to $4,000. There's an application fee, which looks like $2,500 to $5,000, depending on the size of the project. The LDC has 60 days to turn around the application. They then come back with a connection cost agreement, which can look anything like we've seen $250,000 for connection costs. Now, keep in mind, those are for larger community scale projects. Permitting fees with the ESA are more expensive. This process requires commissioning and testing before we energize. It requires an independent engineer, third-party review. It requires that the homeowner carries commercial general liability insurance throughout the life of the system while it's operating. So, as soon as we go over 10 kilowatts, and let's say we've got 7 kilowatts of solar, and we want to add one Tesla Powerwall, which is a 5 kilowatt, which has 5 kilowatts of output power, we're over 10 kilowatts, we trigger this process here. So it's absolutely ridiculous. It's not practical, and it's cost prohibitive for homeowners.
And
so
it's really, sorry to go in there. I've heard that this is something that's really almost specific to Ontario. For instance, in other places, this is not the case. Is that?
So the limit is so this 10 kilowatt limit is specific to Ontario. British Columbia, for instance, allows for up to 150 kilowatts without a connection impact assessment. Quebec, I believe the limit is 50 kilowatts. And it varies sort of across the country by province. Ontario has one of the most restrictive definitions of microgeneration, and this 10 kilowatt limit is pretty unique to Ontario, as is the complexity and the cost of going over 10 kilowatts. So, as homes electrify, and as, especially if we're talking larger homes, and we electrify the home completely, and we want to put an electric vehicle or two in the driveway, 10 kilowatts of PV generation is never going to get that home to net zero. So that's problem one. Problem two is if we want to have any amount of energy storage to back that home up in the event of a grid failure, we're not going to be able to do that under these current guidelines and limitations. Unless the homeowner, and we do, God love them, we have a couple of homeowners that are willing to spend this money so we can put 10, 15 kilowatts of solar and 3-4 Powerwall in the home. But that's a rare individual that can afford that. So, it's a problem. Now, what can we do about it? So Lee mentioned electric vehicle energy management systems. So here's the ESA bulletin. This is Ontario specific, but it does come from CEC, which a lot of provinces simply, they just simply implement the Canadian Electric Code, and they don't have a provincial level one. But this is Ontario, and CEC and OESC has this stipulation here that says that if you put these current limiting conductors, or sort of current monitoring conductors, and there's two scenarios here. So this is our electric vehicle management system, and here's our EV charger. So what these CTs are doing here is they're measuring the total amount of energy that is being consumed in the home, i.e. on this panel. And they're saying that the electric vehicle can use the amount that, so if there's a 100 amp panel, and this EV charger wants to supply, 30 amps to an electric vehicle, and we're already consuming 60 amps in the home because we have an air source heat pump running and something else, then this management system will say not now. And it'll monitor power coming in until it drops, and then it'll allow the EV charger to energize. Up here, this is a different scenario. This is a branch circuit supplying the energy management system, which is sending power between an EV charger and a hot tub. So This is saying we have a max of, let's say, 60 amps of current available. It's going to split up if the hot tub is running, the electric vehicle can't, or vice versa, whichever the priority is. So that's how that works. And that is the code reference in Ontario. And there's a similar one for nationally for the Canadian Electric Code.
Okay.
The other thing that is coming quickly, not quickly enough, and it is an energy management system. Code refers to it as power control systems, and the UL certification is for power control systems. And so these are modules, it's equipment essentially. And in this scenario and in this example, what we're looking at are modules that control individual circuits. And so the circuits are paired through a relevant module of equal ampacity ratings so that, we can do this safely. That then gives the homeowner or whomever the ability to regulate energy consumption in the home by circuit, establish priorities, establish limits, control power flow, and keep total consumption under thresholds as defined by user. Now, Lee had mentioned that there's a whole lot of murkiness in terms of how we can deploy this stuff. This is the most murky. So, don't not put a 400 amp service in if that's what the load calculations say you need right now because you think you want to use something like this. We're not there yet. Hopefully we get there soon. Andy, I'm going to stop there and open it up for questions because that'll probably be much more productive than me continuing.
That's awesome, Will.
Yeah.
No, it's very, very complimentary. That's very complimentary to the presentation. It's sort of a nice segue. We see the possibilities, we see the technologies there, but now when we get into the actual application, dealing it with those of us working on the ground, putting it in homes, it seems that we're back to, there's a whole lot of stuff that's going to have to be fixed, both on the codes, standards, and the regulatory size. I remember even, I think maybe as you will mentioning, just the comfort level of individuals that, again, work with this type of equipment to move from breakers that, that whole mindset that once an old-fashioned breaker shuts off, at least they know it's off, and to move to the thought that a breaker's now going to be controlled by a computer sort of scares them a little bit. Who says it's not going to turn back on and cause issues? So, all right, we are going to go to some Q&A, folks. We've got lots of Q&A. We're going to move through these really quick. So I'm going to read the question, and I might ask just one of you to just go through it, if that's okay, guys. All right. So, Paul just asked a question. He says, in provinces with high energy factors, every time a non-electric furnace is installed, it won't be replaced again for 15 years. Should we encourage heat pump installation anyway, assuming their energy factors will be much better in 10 years? So energy factors are grid emissions, right? We all know the grid, even Alberta is ahead of schedule, shutting down their coal plants, which is sort of cool. I think the idea is, should we not build today in a house with technologies, knowing that the grid, even though it might be high today with emissions, that in the future it's going to go lower? So I think that's his question. Or should we just encourage every air conditioner to be a heat pump to take better advantage of higher SEER factors? So any views from your standpoint on that, Aiden?
Yeah, I mean, I guess I would probably encourage both. I would for sure encourage that heat pumps should be installed instead of air conditioners. And I would also encourage them in any province, but in the provinces with higher emission factors right now, I would maybe pair it with a small PV system to mitigate the impact now, because, we're dealing with the climate change problem. It's on a fairly small time horizon. So carbon emitted today is worse than carbon emitted in 20 years, 10 years, 20 years.
Okay, so, right.
Yeah.
Okay, I got another one. Rick Gratton, nice to have you, Rick, on there. Rick just says, going back to your load analysis there that you showed, Aiden, the winter load, winter load, that peak load, was that based on backup heater loads, or was it based on the load of the heat pump running at like a 1.5 COP?
Yeah, it was the load of the heat pump at that COP, because it was a cold climate heat pump. So
it would be even higher if, say, for instance, the temperatures did drop, and to Rick's point, goes back to in full electric. which again, maybe goes back to that. Maybe it's better instead of going back to electric. Maybe it is better if it goes back to even just a little, sipping away on natural gas, just a little bit. I mean, could be a possibility.
Common kit, Andy, is 10 or 15 kilowatts for backup electric heat.
Ooh.
That's common kit. You got to cover. I know there are some mech designers on this call, but you basically have to cover your design heat load if your heat pump can't cover it. So so you've got to cover it somehow, right? And I want to do a small plug for Aiden and I here. We did our middle of a project right now for a cost of heat pumps, total cost of ownership. And I can tell you 100%, at least on the Ontario time of use thing, you are always winning having a heat pump instead of an air conditioner on the cooling sizing. Always.
Isn't that interesting? Okay, so always, every case, winning with the heat pump as opposed to just an air conditioner. Okay, good. That's another presentation, right? Another day. Joe Rogers made a good point. He shared this over. He says the presentation showed 100 amps at 240 volts. You cannot do this in the home with 100 amps. You'll obviously need to do 200 amp service as a minimum.
Yeah, I might have cut and paste from different presentations. It just missed something there. Sorry about that.
Thanks, Joe. Eagle eye. That's good. Yeah, that's right. And again, what we're finding is that, this is a big deal in new homes to try to keep that threshold at 200 and not rolling over into 400. But what about existing homes that are all at 100? And you have a bunch of 100 amp panels tied to current transformers, branches down the street. That's a big deal. I'm going to go to Justin Bouchard. With respect to vehicle to grid, good to have you too, Justin. Is there an impact on fire rating for new home construction? Interesting.
Nobody has specified that yet. Probably too early. There's a binational standard from CSA and UL that is being adopted by all equipment providers right now. Nobody has called this out respectively in code. There is work being done. So we haven't heard anything on that as it stands right now. Probably very similar to the standard electric vehicle charging as it stands until somebody changes it.
Right. Okay. Next one, Lee, is a little bit maybe for you from Mark Leduc. Says, sounds to me like vehicle to grid is energy quota applied to each house. The implications, again, I think he's referencing, that you use the vehicle energy to then shave your load. He says one day you wake up and now you can't go to the market. An energy cap on the house is a hard sell to the end user. Just comments you want to.
I used a very, very small consumption, right? We're talking 35 kilowatt hours. That's tiny in comparison to a 100 kilowatt hour battery in an electric vehicle, right? So and that's a lot of usage, right? So we could even do this with 10 kilowatt hours. It's quite small.
Yeah, I think that's the thing too. It's hard for me to understand, like Mark too, and is that what we're talking about to shave the grid during these times? We're not talking about massive amounts of electricity. Here's what really causes issues, though, Mark, is if we have to offset that, if we can't shave it, now we've got to generate it downline with 70% transmission losses and during peak times, and we can't do that with nukes because you can't ramp up or down. Now we got to do it with peaker plants. So it's that careful line between how we're going to do this. Rick Trapp, nice to see you, Rick. Does the vehicle to grid charging result in a shorter battery life? Oh, that's interesting. So if something's always going on between the house and the battery, what's the thought there, Lee?
We have heard no. That's the short answer.
Okay.
There's a lot more work done in this in Europe. A variety of manufacturers have already been talking about this. So there's some suppliers in the U.S. that worked out deals with Nissan, no effect on battery life. There's a variety of press releases that come out recently with Kia and a inverter supplier, no effect on warranty. So, and also this is buried in lots of investor literature from the vehicle manufacturers, BMW, Volkswagen, Volvo. They're looking at this as an income stream. So my quick answer is no.
Okay. And that's interesting. I think it goes back to your thought, we're talking about 35 kilowatts, right? We're not talking about massive draws. And, as an electric vehicle owner, we all find out that the more supercharging we do, when we do that, that does hurt the battery, right? But the trickle charging, a few kilowatts don't really hurt it. It's that high heat, the batteries, popping and expanding underneath you. Those are the events that sort of kill you.
And we're talking like 2 kilowatts, right? For feedback. We're not talking much needed to cut these peaks, right? We're not talking much at all.
Yeah. Okay. Awesome. Yeah. Thanks for that, Rick. So Ryder Petch says, this is great info. Do you have a residential pilot study you can share on vehicle to grid as backup power?
I don't right now, but I will shortly.
Okay.
I'm
There you go.
pre-published right now. I think there's some papers. We'll spin that around to the email that goes out after this if we can locate them and pop them in there.
Okay, awesome. Thanks. Good question, Ryder. Pauline, how are you, Pauline? And from BC. Does the vehicle to grid system only work when the EV is plugged in?
Yes.
Okay, that's a good question. Yeah.
It is.
Yeah. Brad said, so considering a net zero home designed with a PV system and with an electric vehicle, and either a EV management system or vehicle to grid, do you supplement the electric vehicle storage capacity for a typical battery storage system? Would that be the idea?
So the actual cost of a vehicle with the battery in it is generally less than the stationary storage system as it stands right now. And you can drive it around. It really depends on the end use. Will might have some, some discussion on this too, but if you're buying a vehicle and you've got that battery in it, you might as well be using it, right? Because you're not driving it around 100% of the day, and you've already paid for it.
Yeah. Will, any comment there?
Yeah, the point was raised earlier in that if you're using your electric vehicle to supply power to the home, it's going to limit the number of kilometers that you have available to drive. And so that's going to be obviously a pretty critical factor in determining sort of how you would use that. But Lee's absolutely right. Like, a Model 3 with 75 kilowatt hour battery bank, in order for us to do that with Powerwall, it would cost more than the Model 3. So, it's interesting. And in addition, code actually prohibits us from putting more than 40 kilowatt hours of stationary storage capacity in a residential dwelling in an attached part of that building, but we can park 300 kilowatt hours of electric vehicle in the driveway, no problem. So, there's lots to consider there.
Bit of a workaround.
I think it's probably maybe a little bit of A and a lot of B, which is like a little bit of stationary storage, because that gives you a lot more flexibility and control of say PV generated power. Without that, PV is pretty dumb and it's either on or off. But with a little bit of storage, you can do a lot more in terms of control, time of use, where it goes. And then the vehicle being the larger storage facility and the ability to supply more power. The choke point though is the EV charger itself. So if the home needs 15 kilowatts and you've got a level 2 EV charger, it can only supply probably 9.6 kilowatts at most. So that's the most amount of power you'll get from a level 2 EV charger and back into the home. And if you've got, air source heat pump, hot water heater, and other loads going on, and you need 12, 14, 16 kilowatts, you're not going to get that from your vehicle. So you're going to need to supplement that with other generation on site. And then we get over that 10 kilowatt threshold pretty quickly, which then makes it cost prohibitive in Ontario. Other provinces, much more friendly. But there's lots to consider there around that.
Just to add on that too, a lot of these as well are DC chargers, so they can go over 10. So the white box there, that goes up to 15 and change, I believe, charge and discharge. But that's the same problem Will talked about.
Yeah, you've got a supply issue, and then on the regulatory side, there's going to be, you've already been down that road once, and there's a lot to get figured out there.
Next question, Rick, again, just a quick question. He says, in Calgary, they were recently informed that a EV charging storage system, as you described, cannot be used in multi-unit buildings utilizing a single electrical feed to multiple meters. So Lee, anything on that?
I haven't read the Alberta interpretation of the code. That's an interesting problem, though I can say, like echoing Will's comments, it really comes down to the person standing with you on the ground making that decision about how they're going to interpret that clause in the code. For the project that I did, I had 9 different people touch points at the AHJ to get that done. So
Oh, and we're still struggling to get building permits within one. Anyway, so we'll go to, okay. So Ryder has a question. Will, you want to take this one? One more question. Are there recommended CSA approved smart panels on the market right now? Any names or brands you want to mention?
Unmute.
There we go. So short answer, yes, there are. So smart panels, there's not an Eaton or a Siemens or a Schneider solution that is a smart panel per se as yet, but there are manufacturers who are making equipment that can be retrofit alongside a typical panel to turn them into a smart panel. There's a company called Lumen that's actually making a smart panel that I think is still going through CSA UL certification. Savant makes some power control modules that integrate into a panel that are CSA that we're deploying in Canada right now. So there's not a single sort of piece of equipment that you put on the wall that is a smart panel that replaces your electric. There is one actually, KSI, sorry, Coben System.
Yeah.
However, it's not something I think that is for the every home type scenario. It's very, I think, niche at this point, but you know, they have an interesting piece of kit there. It's worth having a look at. It is a fully functional all-in-one smart panel that replaces the electric panel. It's limited on total number of circuits. It's limited on max output per circuit. Like it can't supply a 60 amp circuit, for instance. 50 amps is the most. So there's things to think about. So I want to say yes, but it's not as straightforward as that, but it can be done.
Yeah, I see there's Vic, you just noticed Verconic, hope I'm pronouncing that name right, Genius System, UL, CSA, ETL. So yeah. Thanks for that, Vic. I want to start from the bottom up here. We're just coming in at our time. Question was here, are there apps so that homeowners can use that have solar panels, vehicles, vehicles to panels, batteries, and all the controls into one place? Will?
Well, there's not an app. What it requires is a manufacturer to have the equipment that does all of that, then you can access in that one location. And so there are a couple of manufacturers, and you know, that KSI panel doesn't have an app, but it has a desktop interface that you can go in and you can do that with. And there are a couple of others like, you know, Savant, I think, is probably leading in this category right now. Lumen has some interesting stuff coming out. So there's, you know, it's coming and it's coming quickly. And this is what I was referring to, you know, earlier during in that last slide there, is that this is the murkiest of murky, but it's the thing that is accelerating the most quickly and the thing that I think people are most interested, because it's the piece of the puzzle that needs to get put into place for all of this to work.
Yeah, okay. And on the vehicle side, Andy, Wallbox, Quasar 2, and the DC Bell R16 both have home management apps.
Okay, if you want to type that into the chat, that'd be awesome. So thank you. No, that's really good. Thank you, both of you. Alexander asked a very interesting question, and I think it's worth reinforcing this one because, Will, you've answered this, but he asked this question: would a vehicle to grid be considered part of the generation contribution to the size of the system?
Yes.
In taking it over a micro grid system? In other words, if you're 9.9 PV system, then you add that, you would push it past a residential system. That's right? Will?
Yes.
Yep. Sorry.
Yes. Yeah.
Okay.
Unfortunately,
okay.
but yep.
Okay.
Questionable though if it's all managed through one hub. So we have to see how that's interpreted.
Gotcha. So if it's all managed through a control hub, then that's where the questions come. Is yeah. Okay. Okay. Good. Last one. Some last questions here. Really interesting stuff today. Any comments on the Connect DER plug and play meter collar instead of making electrical panel upgrades? I'm not familiar with that term, but okay. All right. We're going to, folks, I'm going to reshare my screen. So you're just going to have to hold on tight here real quick. We are coming up on time. Hopefully you can see that. Thanks everybody for joining us today. I do want to catch everybody's attention before they leave though. Our next session coming up in October the 12th, we've got both the Canadian Wood Council and the APA joining us, Corey McCambridge, Robert Jonkman, VP there at Canadian Wood Council, talking to us about what's coming down the chute with the building codes on structural wood design for Part 9. And it's not just things happening in 2024 or 2025, it's actually beyond that. As we look at changing weather patterns, loads, I would say that we're going to start to see some significant changes. We're going to hear from them when it comes to having to make houses and buildings a bit more resilient against wind and water and snow loads. The other thing too, folks, I do want to just remind everybody is we have a session, a 3-part session sponsored by Enbridge that is around the brand new Ontario harmonization with the Part 9. However, we are still waiting on the Ministry of Municipal Affairs and Housing to release their final amendments and timing and everything else. So hang tight, you can still register, but those dates will be identified and sent out as soon as we have the last from the ministry. Keep in mind too, we've got a Builder's Digest, a Building Knowledge Builder's Digest that goes out. We've got another one coming up, so sign up, and it's got a bunch of stuff like we heard today. It's got information on builders. You're going to see a couple cool projects from builders identified in theirs too. And but most importantly, Will, Lee, Aiden, this has really been a good session. Like, thank you folks for joining us today. All 3 of you.
Thanks for having us.
Thanks for letting us harp on the issue.
That's all right. Good deal.
Pleasure to be here.
So we're going to say good day to all of you folks. Keep your eye on our website. Make sure you visit the Blue Water Energy website, Will's team that works out of Central Ontario, and then Lee and Aiden on the Volta, their company and website and the projects they're working on as well. So thanks again, folks, and thank you folks for tuning in, and you'll soon get a copy of the presentation today. But have a very good Thursday afternoon, and we'll see you next time. Thank you.
Thanks.